Hi, good evening. So we'll wait for 2 more minutes. Okay. Okay. Good evening, all. So, so before starting today's class, do you have any doubts in the previous class? In the last class, we saw about the introduction to algorithm. So we saw what is an algorithm and what are the factors we use to analyze an algorithm. We saw the different cases, best case, average case, and worst case. And we saw the different time complexities. Okay, the first one was order of 1, then log n, n log n square, and then non-polynomial complexities. And then we saw about complexity reduction, and we took an example of finding whether a given number is prime or not. And then this was the initial algorithm, which took n minus 2 time. Okay, and then we reduced it by 2. Okay, by reducing the number of reducing the range of the for loop by 2, and then we took only the odd numbers for comparison, and then we further reduced it to n by 2 by 4. And we saw another example, okay, where you'll be given with a string and then you have to check whether all the characters are unique. Print just yes or no. Okay, if all the characters are unique, print yes, else you print a no. Okay, and we saw the various algorithms. The first algorithm which we saw was order of n square. Okay, then we saw an algorithm which will take only order of n, where we take additional memory or additional list as a flag. Okay, and then we just iterate once and then mark all the occurring variables, occurring characters. If that character repeats, we just like return that it is no. I hope you understood. And then you also saw like further reduction. Yeah, so this one using bitwise operators. Okay, we had a flag integer itself. So in the previous example, we had a flag um, array, right? Okay, we had a flag array, not this one. It's not available. Okay, so we had a flag array. In that flag array, we just marked yes or no, present or not. So whereas here we just use a single integer to represent whether the element is present or not. And then we saw about time space trade-off. Time space trade-off is nothing but if you want a algorithm to perform better with respect to time, you have to compensate with space. And if you want an algorithm to perform better with respect to space, we have to compensate with time. Okay, this is time space trade-off. And then we saw an example. First one was the swapping algorithm, where we used a temporary variable to swap two variables. And then here, without using temporary variables, swapping two variables. And we saw the amount of memory and time taken in both these algorithms. And this was an example for time space trade-off. And we also saw Fibonacci example, okay, where we were able to reduce so many calculations if an additional memory was utilized to store the calculated values. And then we saw the different algorithmic strategies. The first strategy to be followed is mathematical formulation. If it is not possible, then we try to apply these strategies. If this is also not possible, then we go for brute force method. Yeah, and we saw two examples. Yeah. So shall we proceed with today's class? Okay. So today we'll see certain searching algorithms, two searching algorithms there, and then we'll see some sorting algorithms. Okay. Searching and sorting. Okay, fine. So before getting into searching and sorting algorithms, let me give an introduction about divide and conquer. So because we're going to see two algorithms on this topic today itself. Okay, divide and conquer. Okay, so what do you think would be this divide and conquer? Divide and conquer. So by the name itself, we are able to get an idea, right? Like we are trying to divide something and then solve it, and then we will try to combine those solutions which after solving the smaller things, right? That is what is divide and conquer, right? So what is that thing? So are we trying to divide a problem into smaller subproblems? Is it so? Are we trying to divide a problem to subproblems? Okay. So actually not. We are in this divide and conquer strategy. That is a different perspective that everyone is having. Here we won't divide the problem, whereas we divide the data set. So we won't be having a solvable data set. Okay, so what we do is we just divide the data set into smaller data set which is solvable, and then we will solve that, okay, the smaller data set, and then we combine the solution obtained from the smaller data set. So that is actually divide and conquer strategy. Okay. So divide and conquer strategy, you can see this divide and conquer strategy in a lot of real-time scenarios. Okay. So in the earlier time, kings were there, right? So they used to conquer the go to different kingdoms and then conquer the different kingdoms, right? So that also they use divide and conquer. So they have a like suppose the if the enemy kingdom is surrounded with a lot of different landscapes. So one side with plain, one side with mountain, one side with the sea. Okay, so he cannot apply the same strategy on the different landscapes, right? So if it is plain, it is bit easy. He can use horse force and then human force and then do it. So if it is surrounded with mountain, so he has to use a different force, right? So he has to use some heavy uh, animals like elephants. So if it is surrounded with the sea, so in that area he will use a different strategy. So he use the navy like that. Okay, so what he does is the larger kingdom is there. that would be split into smaller regions, and he will apply different strategies on different regions. Okay, here the data set is what? The larger kingdom. He is dividing the data set into smaller regions and then applying the strategy on each and every region. Okay, this is one thing, one good example. Other example is in the jungles, of buffaloes. Okay, so will a lion be able to attack a huge herd of buffalo? If it is a huge herd, no, right? It will be killed by the buffaloes. So what it has to do? It has to target on the weaker ones. Okay, it has to apply some strategy to divide that crowd into smaller crowd, right? So what it does, it starts chasing the huge crowd. So whichever buffaloes are stronger enough will move very fast and then move forward. The weaker ones, okay, maybe the old ones or very young ones or like injured ones will travel very slowly. So they get separated out from the herd. Okay, now it is easy for the lion to attack the weaker ones, right? So what it is, its target is to get a meal, right? Okay, so it is not that it has to go and take the strongest buffalo and attack it, right? So its main aim is to get a meal. So it will achieve by applying a strategy. Fine. There also you can see divide and conquer. So here the data set is what? The huge herd of buffaloes. So it will somehow try to divide that huge herd of buffaloes to smaller herd. Okay, which is attackable. Okay. There also you can see divide and conquer. And so in olden days and all, you can see grandmas cleaning the rice. She will keep a huge sack of rice. So how will she clean? Nowadays machines are there, easily they can clean, right? So those days it was manual. Okay, so they have to do every cleaning process manually. So she will not put her hand straight away into the huge sack of rice and then clean it, right? So she take a small lump of small part of the rice, clean it, and then she keeps on gathering the clean rice in a separate place. Okay, she is dividing the huge sack of rice into small pieces small quantities of rice which is solvable, and then she moves the solved um, solved rice, okay, that is cleaned rice, to another different position. Okay, so in all these areas we can find divide and conquer. This is what is divide and conquer. Okay, so the data set is being divided, not the problem is not divided. So I can give you an example where the problem is divided, where that is not a divide and conquer strategy. That is some other different strategy. You can name it whatever you want. Okay, so an example where the problem is divided into subproblems is, you can take the case of marriages. Okay, so marriage is a very big problem, right? Okay, so that problem will get divided into smaller problems like typing invitation, taking dresses, okay, catering, okay, and hospitality, booking of the hall. Okay, so all those things are there. So all these things are small problems. So if we solve all these problems, the larger problem, the marriage, will get solved. Okay, so that is a different strategy, which is not divide and conquer strategy. Okay, I hope you understood what exactly is divide and conquer. In divide and conquer, the data set is being divided, not the problem. Okay, okay, fine. Now, first, let us see searching algorithms. In searching algorithms, we have two searching algorithms. One is linear search and binary search. So linear search is very simple. Like you have a list of elements in some random order. Okay, so what you do is you keep on searching one by one. Okay, so it starts from the zeroth element. So list index will start from zero, right? So you start from the zeroth element. You keep on searching every element. Whenever you find an element, you just return the index of that particular element. Okay, so that is linear search. I think you not much difficulty in linear search, right? Next is binary search. In binary search, the input is sorted array, sorted or sorted list or sorted array, whatever you can call it. So input itself is a sorted list. Now let me explain in the Excel sheet. So this binary search, the strategy that is followed is divide and conquer. And in divide and conquer, there are three steps. One is divide, second is conquer, third is combine. You can also call it as merge. Okay. So in all divide and conquer problems, these two steps will definitely be there. And this based on cases. Okay, if it is needed, this combine step will be there. Else combine step will not be there. Okay. So this is not mandatory or optional. Okay, not all problems of divide and conquer will have this step. Okay, this binary search is an example of divide and conquer where this combine step is not there. Okay, and then merge sort is an example for divide and conquer where this combine step is there. Okay, we'll discuss both these problems. Okay, so input should be a sorted array. Okay, so as if what you do in binary search is that, so we know that it is sorted. Okay, suppose you are searching for the element 56. Okay, now the first step what you're going to do is we're going to find the mid element. Okay, so how to find the mid element? So first you need to find the index of the mid element. Sorry. So what would be the index of the mid element is, you can just use a formula. Okay, you have the lower index and you have the higher index. So it is very simple. Lower plus high divided by 2. That will give you the mid element, right? So it is just like finding the average. So what is low plus high by 2? And it should be a modulo division, not modulo division, floor division. Because we don't need the decimal points because index is going to be a whole number, right? Okay. So low is 0, high is 7. So 0 plus 7 is 7. Floor division 2 is 3. Okay. Now we take the center element and then now you compare the element with the key. Key is nothing but the search element, the element to be searched. So take the mid element and compare it with the key. If both are matching, then you can return the index m. M is nothing but the index which holds the element which is being searched, right? So 56 was searched and you have found the mid element, found that the element is present at mth index, so you can return m. Okay. So now suppose if this is 56, we directly found the mid element and then we returned. But suppose if it was 90, now the search element is 90. Now what happens? So now the mid element is 56 only. If I check whether the search element and the mid element are same, they're not same, right? Next step, what I would do is I'll check whether it is greater than the mid element. Okay. So if it is greater than or less than. So if it is greater than mid element, definitely the search element is not going to be present in the left hand side because it is already sorted, right? So it has to be present in the right hand side only. If at all, if it is present, it should be present in the right hand side because key is greater than the mid element, right? Now what happens is my data set gets reduced to half. I'll just avoid these elements, omit these elements. Okay, only these elements would be coming into picture in the next iteration. So now what happens? Yeah, very good. So now the lower index becomes 4 and the higher index becomes 7. Again, you have to calculate the mid value. So if you apply L plus H divided by 2, so what is L? 4. What is H? 7. Okay, 4 plus 7 divided by 2. What is the answer? 11 floor division 2. 5, right? Okay. So 11 floor division 2 is 5. So now the mid element is 5. Now again do the same comparison. Key is 90. Mid element is also 90. Now search element is found. So we can directly return M, which is 5. Got it? Okay. So now this is what will happen if I search for 90. Suppose if I search for an element that is not at all present. So I'm searching for 91. Let's suppose my key is 91. So till this, okay. So now what happens? First I'll check with the initial data set. Mid element is 56. I'll compare with 91. 91 is greater than 56. So I'll come to the right hand side. So here my mid element was index 5. I compare with the key 90 and 91. So here what happens? Not matching. So next is I'll check whether it is greater. Yes, it is greater. So I'll come to the right hand side. So now left hand side is omitted. Okay. So if I come to the right hand side, my data set gets reduced to 95 and 99. You can notice that the mid element is not taken into account in the next step, right? Okay, because we've already compared. So now the low becomes 6 and then the high becomes 7. So if we apply this L plus H by 2, what is the value? Yeah, 6. Okay, 6 plus 7 is 13. 13 floor division 2 is 6. Now the mid element is also 6 only. If I compare this 95 with 91, it is not equal. Okay, I check whether the key is greater than the mid element. No, it is not greater than the mid element. So it is less than the mid element. So I'll consider the left hand side of 95. So since there is no left hand side, no elements in the left hand side of 95, so we can tell that element is not found. Okay, fine. So within how many comparisons you have done? 1, 2, 3. Okay, with 3 comparisons, we are able to tell that element is not found. So this is binary search, right? So if we use normal linear search for this set, if I want to check whether element is not found, so I have to check for the entire array. 8 times I have to compare, right? Then only I'll come to know that element is not found. Understood? So this is the basic like illustration of binary search. Any doubts in this? Shall we go to the implementation? Okay. Okay. So I told you this binary search is a divide and conquer algorithm. All the divide and conquer algorithms will be recursive algorithms. Okay. We can write it in iteration so, but it is very simple if you write it using recursion. Okay. So for binary search, what all things need to be passed are I'll just write the pseudocode. Okay. So binary search. So we need a list. Okay. So which contains the elements. I'll mark it as A because I have L and H, which are going to denote the lower index and higher index. L, comma, H. So what is this initial, what are these initial values of L and H going to be? Yes, what are the initial values of L and H? L is 0, okay. H is, yeah, H is actually the length of the list minus 1. Okay, see here, total length is 8. Okay, so length of the list minus 1. So that is the initial values of L and H. Now the first step after entering into the binary search is we have to find out the mid element. Okay, so before that, only if we have elements with us. Okay, so in this last step, if in the left hand side of 95, there are no elements at all, right? Only if we have elements, we'll be able to find out the mid element. Okay, so what is the condition? So when will we know that like element is present or not? That has to be done using the values of the index. Okay, L and H. The values of L and H should be used to find whether elements are present or not, or how many elements are present, like that. Fine. So now every time what happens here is, see here, like in the first step, M was 3, okay? M is 3. Since we found out that K is greater than uh, M's value, M 56, okay? That is the value at M. We made L point to the next of M, right? The next value of M. So what happened here? L became 4 and then H was the same. Okay, so here also, like we know that 91 is greater than the center element. So we made L point to the next index of M. So if the element is less than the mid element, what will happen is L would be the same and then H would become one element less than M, right? One element before M. So if I take the element, the index before M, the index would be 5, right? So the next iteration, L would be 6 only, the same element, and then H would point to the index which is less than L. Got it? So you can see an overlap, right? So actually H should be to the right hand side of L. That's why it is called as high, low and high. Okay. So since the element which you are searching is less than the mid element, we have to pass the H value as 1 minus M, and then the low value would be the same as the previous value. Okay, so L is 6 only, but H is M minus 1, which is 6. Okay, so now there is an overlap. H is overlapping L, which means that there are no elements at all. So this is going to be our condition. Okay, so if H is less than L, you can return none. Or if you want, you can return negative index also. Since in Python we have the none option that could be returned, we can return none. In other languages, C and Java, we will be returning the negative index, which means that element is not found. Okay, so here we can return none. So okay, so if this condition is false, what does it mean? It means we have some more elements left out that has to be processed. Okay, so now what you have to do is the first step itself, you have to find out the mid value. Only if we have the mid value, we can compare the element, right? And most importantly, you have to pass the key also, the element to be searched. Don't forget this. Fine. Now mid element, mid index. Okay, mid is equal to L plus H, the same formula that we discussed. Next, what we do, we just compare this mid element, okay, with key. If key is equal to a of m, so what should we return? What should we return? We are returning the index of the element where it is present. So what should be returned? Yes. K is equal to a of m means what? K is located at the nth index only, no? So return m. Are you able to follow? Any doubts in this? Yes, any doubts? Okay. So return m. So if you have found the element, return m. If the element is not found, either it should be in the left hand side or in the right hand side. So just compare with the mid element and then do the proper recursive calls. Okay. So if key is greater than a of m, it means that element is present in the right hand side. Okay. So now we are going to call the right side recursive call. So return. So this binary search, whatever I'm calling, that would return some value, right? That has to be returned to the previous function and that will be returned to the previous. Like that it goes on because it is recursive call. Okay, don't forget this return. If you forget this return and finally none only will be returned. Okay, be careful with this return. Binary search of a comma. So now what should we pass if k, the element to be searched, is present in the right hand side? In place of L and H, what should be passed? Is it M and H or M plus 1 and H? Mid element is not going to be considered the next time, next recursive call. So yeah, so it is M plus 1. So mid index plus 1, which is going to be, which is going to act as the lower index for the next recursive call. Okay, comma H. So else, so if this condition fails, it means element is present in the left hand side. Okay, return and key. Binary search of a comma. What should be passed left hand side? Low value and high value. Yeah. So L comma M minus 1. That's it. Okay, so this is your binary search algorithm. Now let us try to calculate the complexity of this algorithm. We already know that the complexity of binary search is log n. Let us try to derive the complexity of binary search algorithm. Okay. And now, like for all the recursive functions, not only for this binary search, for all the recursive functions, there is something called recurrence relation. Okay. So it is nothing but like we're going to calculate time for each and every condition. So that is called recurrence relation. I'll tell you how to derive this recurrence relation also. See, recurrence relation, like it is going to like give you so if the data set is going to be like number of elements is 1, what's the time taken? Number of elements is 2, what's the time taken? So if there is a general case, for that how much time it will take? Like that, step by step defining the time, that is called recurrence relation. So now let us do it for binary search. Okay, T of n is nothing but the number of elements. Okay, is equal to, so now if number of elements is 0, Okay, if n is equal to 0, I'll just write symbol equal to. If n is equal to 0, means number of elements is 0. Are we doing any operation? Nothing, right? We simply return none. Okay, for returning, there is no time. We are assuming that there is no time taken. Okay, so the time taken would be 0. Understood? If number of elements is 0, we're not going to proceed at all, directly return none. So time taken is 0. So if number of elements is 1, what happens? There are two conditions if number of elements is 1. Either the element is present or it is not present. Got it? Either the element is present or it is not present. So here, once we found out that there are few elements, okay, immediately we are finding out the mid element. So for finding the mid element, it is a constant time, right? So we're just doing a addition and then a division. So two operations are happening. So it will take a constant amount of time, right? So for that, let us write 1. So which means that 1 unit of time. So constant can be represented using 1 or C. Okay, for simplicity, let us write it as 1 itself. Okay, and now suppose I told you that if there is only one element, what are you going to do, right? So if there is only one element, either this condition satisfies. If this condition satisfies, it means what? The element is present at that particular index. We are returning m, right? So for returning, there is no time taken at all. So plus 0. Okay. So if element present. Understood? So if element is not present, what happens? Either it will go to the left hand side satisfying this condition, or it will go to the right hand side satisfying coming to the else part, right? So like if there is only one element and right, if it whether it goes to the right side or left side doesn't matter, right? Because both the sides there are no elements. I repeat again, if there is only one element and if that element is not equal to the element key element, okay, key is not matching with that one element, so either it will go to the left hand side or it will come to the right hand side. Okay, so if it goes to the left hand side, there also no data is present. If it goes to the right hand side, there also no data are present, 0 elements are present. So we know for 0 element it is also going to be returned, it is also going to be 0. So here also, if the element is not present also, it is 1 plus 0 only. Okay, 1 for this calculation and 0 for returning none, going to the next step and returning none. Okay, so like we can write this as a general value. Did you get this? Any doubts in this? If n is equal to 1, even if it is present or not present, the time is going to be 1 only. Okay, 1 plus 0 is 1 only. Any doubts in this particular line? Understood why I written 1 for n is equal to 1? Yes? Okay, fine. Now, if number of elements is not 1, okay, so I'll repeat once again. So like if the number of elements is 1, let us search for 99. Okay. So till this step, it is fine. Now what happens? The next step, okay, so here mid element was 95. Comparing 95 with 99, it is not equal. So it key is greater than the mid element. So we have to go to the right hand side. So right hand side, if we come, there is only one element, 99. Okay, so L and H both are going to be pointing to the same position. All right. Okay. So L and H both are going to point to the same position. So now what is mid value? And the index is 7, right? So L plus H is 7. So mid is also 7 only. So 14 by 2 is 7. Okay, fine. So now mid element is 7. So mid element, see if there is only one element. So mid element is equal to K. So what I would do, I will calculate the mid value, and then I will return 7. Understood? So for calculating the mid value, I'll take one time unit. So for calculating the mid value, I'll take one time unit. And then for returning, okay, there is no operations at all. Directly return some value, right? So there is no operations. So just plus 0. This is when the element is present. Okay. So now I'm searching for 100. Now what happens? Mid value is 99. Okay. Comparing with 100, it is not equal to the mid value. So it is greater than the mid value. So it has to go to the right hand side. So right hand side, if it goes, again, this is a single value, single element, right? For single element also, again, I have to find the mid value. After finding the mid value only, I'm going to the right hand side. Okay, so if I go to the right hand side, there is no data at all. So I have to return none. Understood? So either I would return 7 or the next step I return none. And we know that for if number of elements is 0, the time taken is going to be 0 only. So like 1 for calculating the mid value plus 0 for number of elements is 0. Now did you get this? This is positive case. If element is found, positive means element is found. This is negative. Element is not found. Okay, so that is why in general I wrote if number of elements is 1, the total time taken is going to be 1 only. Okay. Now, so if I have more elements, okay. So now what I have to do? And if I have more elements and I don't have, the mid element is not matching. So what I will do? Either I will go to the left hand side of or right hand side of. Left half or right half I'll go. Right? I'll just skip the entire half based on the condition. I'll skip the left half or the right half. Right? So what happens? My time will get reduced to half. Right? So my number of data is going to be half. So time also will be reduced by half. Right? So if there are more elements, so I have one time unit to calculate the mid value, and I will go to the right hand side or left hand side, taking only half of the data set, which gives me half of the time. So this one is for calculating the mid value, and this T of n by 2 is for any of the halves, either right half or the left half. Understood how this is 1 plus T of n by 2? Yes. So we'll find the mid value. Okay. And then we'll either go to the left hand side or go to the right hand side. See, if I'm going to going to process both the left half and the right half, then what happens? It would be 2 T of n by 2, right? So time to evaluate n by 2 elements. Okay. So if both halves are going to be processed, then it is going to be 2 T of n by 2. Here, it is an if-else condition, either left half or the right half. Okay. So that's why it is T of n by 2. Got it? Any doubts in this? Did you understand how to formulate the recurrence relation? So we had only two. We were able to formulate only three different cases, right? If number of elements is 0 and number of elements is 1, and otherwise more elements are present. Okay, so based on the problem, it varies. Number of steps varies. Fine. So any doubts in this? Using this only, we're going to calculate the complexity. Are you able to follow?
Yes, sir.
Okay. Fine. So now let us proceed and use this recurrence relation to find out the complexity of the algorithm. So to find the complexity of this algorithm, we're going to check for each level what is going to happen. Okay. So at level 1, okay, so this is at level 1. So this T of n became T of 1 plus, okay, sorry. Yeah. So T of n became 1 plus T of n by 2, right? So the second level, so what will happen to this T of n by 2 in the next level? See, initially I had 8 elements. The next step, I had only 4 elements. Okay. So in the next step, what will happen? That 4 elements will get converted to 2 elements, right? It keeps on getting divided. Okay. So what is T of n by 2?
T of n by 4 then.
Yeah. So if T of n is 1 plus T of n by 2, what is T of n by 2? It is 1 plus T of n by 2, another by 2, right? By 2 whole divided by 2. Which is nothing but 1 plus T of n by 4. Understood? So just substitute this over here. Now what happens at level 2? It becomes 1 plus. So instead of T of n by 2, I'm going to substitute 1 plus T of n by 4. Okay. So 1 plus T of n by 4, which is nothing but 2 plus T of n by 4. Okay. Fine. Now in the next level, what will happen to this T of n by 4? We can find it out. So what is T of n by 4? If T of n is 1 plus T of n by 2, T of n by 4 is 1 plus, just substitute in place of this n, substitute n by 4. Okay, n divided by 4 whole divided by 2, right? Which is equal to 1 plus T of n divided by 8. So now just substitute this 1 plus T of n by 8 in this T of n by 4. That would be your level 3. Okay, so 1 plus, sorry, 2 plus. So from here only we are going to level 3, right? Okay, 2 plus, in place of this T of n by 4, substitute this 1 plus T of n by 8, which would become 3 plus T of n by 8. Fine. So now what would be level 4? Can you tell me without calculating? Yeah. So that is the general formula Abhishek has given. So it is 4 plus T of n divided by 16. Right? At level K, it is going to be K plus T of n divided by 2 to the power K. That's all. So this is your general formula. So once we found out the general formula, so what would be at the last level? So at the last level, what do you think would be 2 power K? So all it is going to, in the last level, it is going to be individual element, right? One element. If you consider one element, okay, so how many single elements are going to be there? See, so let us see the general divide and conquer. Suppose there are 8 elements. Okay. So now what happens? This 8 elements will get split into 4 elements and 4 elements. Right? This is at the level 2. And now what happens? These 4 elements will get divided into two elements, and these 4 elements also will get divided into two elements. Now next level what happens? These elements will get divided into individual elements. Okay, this is at the last level, which is level 3, right? Okay, this is level 1, level 2, level 3. So here, what is 2 power 3? It's 8, right? Okay. So at the last level, okay, what is 2, 2 to the power 2 raised to the last level, which is nothing but total number of elements, right? So these elements are only getting split into individual elements, right? So the last level, 2 power 3, that is 2 power k, would be equal to n if k is equal to last level. Are you able? Did you understand this? Okay. So if 2 power k is equal to n, so what is k? If 2 power k is equal to n, what is k? Log n, right? Okay, taking log on both the sides. So log 2 power k and log n. Okay, and yeah, obviously it is base 2. Okay, so log 2 power k is k, right? And then log n is log n only. Understood? So k is equal to log n. Now just substitute these two values in this place. Okay, in this place, you just substitute these two values. So in place of k, substitute log n. In place of 2 per k, substitute n. So k is log n plus t of n divided by 2 per k is n only. Understood? Okay. So what is t of n by n? T of 1. Log n plus t of 1. So what is t of 1? We already know if n is 1, time taken is only 1. Right? So in place of 1, just substitute 1. So in place of t of 1, substitute 1. So this is the complexity of binary search algorithm. Okay. So since log n is of higher order than 1, we can just consider this order of log n. Understood? So for any recursive function, you will be able to derive this recurrence relation. And using this recurrence relation, Just do 2 or 3 steps and then try to formulate the general formula, and then you can derive using the general formula, you can derive the complexity. Okay, so even for merge sort, we'll be looking into this derivation of the complexity. So just note it down and then you can just go through it once again to understand it better. Okay, fine. So I told you that in divide and conquer, there are these 3 steps, right? And this binary search, the third step is not there. Can you tell me which is the divide step and which is the conquer step in this binary search? There's a shortcut to find this. Okay, the thing is, always a recursive calls would be the divide step. Understood? So here is where you are dividing the data into half, right? Either the right hand side off or the left hand side off. You are dividing the data. So always the recursive calls would be your divide step. And these stopping conditions are there, right? Okay, all the return conditions, stopping conditions or base conditions would be your conquer step. Okay, so divide is the recursive calls and conquer is base conditions. Understood? So by seeing the algorithm itself, we can tell which is the divide step and which is the conquer step. Fine. Yeah. So now let us go to the sorting algorithms. So basic 3 sorting algorithms are there. One is the bubble sort, insertion sort, selection sort. Okay, so these 3 algorithms are order of n square algorithms. That's why I grouped it together. And there is one more algorithm that we'll be discussing, which is merge sort. We'll come to that later. Okay. Now, like we will discuss bubble sort and insertion sort, and I would give it as an assignment for you to see what is selection sort. Okay, next class we'll discuss. I want you people to understand what is selection sort and come the next class. Fine. So first let us see bubble sort. So once you see the algorithm, you will figure out why this bubble is the name of the algorithm. Okay. So we are taking some random elements. Okay. So let us take these 6 elements. So in bubble sort, what we're going to do is we are just going to compare the adjacent elements. Okay. So if the adjacent elements are not matching with the condition is in suppose we are trying to sort it in ascending order. Okay. So in ascending order means like the final output should be 1, 2, 12, 15, 34, 56, right? So now we can see the adjacent elements, they are not in order. So if they are not in order, immediately do a swapping. Okay. So now 12 and 1 are not in order. So swap. So now what happens? first and second element are compared. Now they got interchanged, and now this is the second element and this is the third element. Compare the second and third element. Are they in order? Yes, they are in order. So go to the next step. 15 and 34, are they in order? Yes, they are in order. So go to the next step. 34 and 56, yes, they are in order. So go to the next step. 56 and 2, they are not in order. So swap. So 1, 12, 15, 34, 2 and 56. So this is the end of the first iteration. In the first iteration, can you see it has brought the largest element to its position. Okay, largest element should come to the last position, right? So the largest element has come to its position. Now in the next iteration, we did not include this into consideration, right? Because it is already come to its position and it is the largest element also. If we compare the previous element, it is an unnecessary comparison because no swap is going to happen because it is the largest element. Okay, so now we will go to the second iteration. Second iteration also, you're going to repeat the same process, but you're going to consider only the first 5 elements, leaving the last element. So now 1 and 12, comparing these both, they are in order. 12 and 15 in order. 15 and 34 in order. 34 and 2, they are not in order. So now what happens? 1, 12, 15, 2 and 34. They will get swapped. And then 56. The element which is already there. Now this is the end of the second iteration. And you can see the second last element has come to its position. Okay. The second last element has come to its position. Now in the third iteration, we did not consider the last 2 elements at all because they are already in order. Okay. So only these 4 elements you have to consider and then proceed with the next step. So the next step, we have these 4 elements. So compare 1 and 12, they are in order. 12 and 15 in order. 15 and 2 not in order. So swap. And then these 2 elements we did not consider at all because they are already sorted. Now this is the end of the third iteration. I can see the third largest element has come to its position. Okay. Now in the second and in the next iteration, which is the fourth iteration, we did not consider these 3 elements at all because they are already sorted. Now compare 1 and 12, they are already sort, they are in order, so no swap. 12 and 2, not in order, so swap. And these 3 elements as it is. So you can see this is the end of the fourth iteration and the last 4 elements are already sorted. Okay. And these 2 elements, we need to check whether they are sorted or not. If not, we have to swap. Now the last iteration. So these 2 elements are sorted. So no swap. And the next iteration, we can see 2 has come to its position, right? So last 5 elements are in its position already. So if there are only 6 elements, if all the the 5 elements are sorted, definitely the sixth element also would be in its position, right? So we need not proceed. We need not take the last iteration at all because there's only one element and there's no other element to compare with. So this is bubble sort. So every time a new element, sorry, every time in the iteration, okay, the largest element will come to its position. Understood? Okay. So any doubts in this bubble sort? This is an illustration of bubble sort. Okay. So it's all right, Sam. I will send you the YouTube link. Okay. Fine. Now let us try to implement it. So if you see the implementation, okay. So So what should be the range of the first for loop? If number of elements is n, yes, what should be the range of the first for loop? So it should see how many times these iterations are happening. 5 times, right? If there are 6 elements, 5 times it is happening. Why it is happening 5 times is that you can see the last iteration there will be only one element left out. Okay, so like if there is only one element, we already know that it is sorted, right? Even though if we consider, so it is not going to run at all. So we can write 0 comma n minus 1. Okay, fine. So 0 comma n minus 1, that would be the number of times this loop will run. Understood, right? Why I'm writing n minus 1? I'm reducing one iteration because the last iteration there's going to be only one element which has to be checked. If there is only one element, it would be already sorted. No need to compare at all, right? So that's why it is n minus 1. Even if you put n also, it will work correctly. But unnecessary one extra iteration will happen with no operations. That's why here itself we are putting n minus 1. Now next is the j loop. So what should be the j loop range? So here you can see it is starting from 0th position and it is going till n minus 1. Why? Because we are just comparing the adjacent elements, right? If we go till the last element, what happens? There is no element to compare with, right? Next element is empty. So we should stop here itself. Then only we can do a comparison with the last element. Are you able to follow? If you go to the last element, what happens? There is no element after the last element to compare with. So that will throw an error. Okay. So index out of bound error will occur. So what you have to do? You have to stop here itself. So here what we're doing, we're comparing 0th element with first element with second element, right? Adjacent elements are being compared. So j in range 0 comma again n minus 1, and there is one additional term that should come. What is that is every time after the end of the iteration, you have one element that would be sorted. So in the first iteration, 56 got sorted. Second iteration, 34 and 56 got sorted. Third iteration, 15, 34, 56. So every iteration, one element is getting sorted, right? So in the next iteration, I need not consider 56 at all. Okay. In the third iteration, I need not consider 34 and 56 at all. The fourth iteration, I need not consider three elements at all. So I have a track of the number of elements in I. So I'll just put minus I. Understood why I'm putting minus I? Yes. So every time I have to reduce the number of comparisons in the J loop. I have to stop here itself. That's why minus I. And so what is the logic inside the J loop? I'm just comparing the adjacent elements, right? So if A of A is the array, okay? A is a list, right? Capital A. A of J, if it is greater than A of J plus 1. So these are the adjacent elements, right? Swap A of J and A of J plus 1. That's all. Understood? This is your bubble sort algorithm. So the swapping, you have to write the logic, okay? So you know how to swap two elements using temporary variable, without using temporary variable. We discussed in the last class, right? So you can write a function separately or you can write the steps here itself. No. So any doubts in this? Did you understand bubble sort?
Yes, sir.
Okay. So now let us try to understand the complexity of the algorithm. So the complexity of the algorithm is going to be like, let us see, actually it is order of n square, worst case complexity. And the best case complexity is order of n. I'll tell you how it is order of n. So first, now here it is. How many comparisons are you doing? The J loop, the number of elements is 6. The first iteration, how many comparisons are you doing?
5.
5. Yeah. So here we have omitted the last element. So how many comparisons are we doing?
4.
Yes, 4. And the last two elements are omitted. So here
3.
3,
2.
2, and
1.
then 1. So isn't it similar to the complex that we discussed in the last class? So 5, 4, 3, 2, 1. If the number of elements is 6. So sum of n minus 1 natural numbers, n into n minus 1 by 2. So the order is going to be order of n square. So this is the worst case. Now coming to the best case. Okay. So for converting this algorithm to the to perform well using best case, we have to do some modification. I'll tell you what is that. See, suppose you take this algorithm, you take this data. So you take this data. Now, if you are performing sorting in this data is already sorted. Okay. Now what happens? We'll just do a comparison with 1 and 2. They're already in order. 2 and 12, they're in order. 12 and 15 in order. 15 and 34 in order. 34 and 56 also in order. Understood? So everything is in order, right? There was no swapping at all that happened. If that is the case, then immediately you can stop without proceeding to the next iteration. We can straight away tell that it is already sorted. We need not proceed to the next iteration and go till the last. Okay. So here itself, we can stop and then tell that it is already sorted. Fine. So for that, what modification we're going to do is we're going to have a flag variable. I set it as 0. And if there happens any swapping, I'll just set the flag as 1 to denote that swapping happened. Okay. So after coming out of this J loop, I check whether any swapping happened at all. Okay. So if flag is still 0, okay, which means what? The if condition was not satisfied at all, and then the flag was not set. If the flag was not set, which means no swapping happened. If no swapping happened, already sorted. So we can break here itself. Understood this? I'm just keeping a note whether any swapping is happening or not. If no swapping happens, already sorted. So it can be at the intermediate step also. It need not be the first step. The intermediate step, suppose after doing 2 iterations, third iterations, the element might have got sorted. So if I find that it is sorted in the third iteration, I need not proceed with fourth and fifth iterations, right? I can save 2 steps, 2 iterations. So that is what we are trying to do here. So in this way, the best case algorithm complexity would become order of n. Why? Because we're just doing a single iteration where the adjacent elements are compared. And 5 comparisons will happen and no swapping will happen. So the complexity is order of n. Understood? So this is worst case. Best case is order of n. Small o, okay? Any doubts?
So,
Yeah.
so You're saying that flag, if even this particular, for the first step, if flag is 0, you've written break. Okay. Uh, and
Yeah,
if you said that even after 2 steps also, this can happen, this situation can occur.
yeah.
So this I'm not able to follow. Like even if it swaps once, then the flag will change to 1. No.
No, yeah. Every time I'm setting the flag as 0, right? Before starting of the J loop.
Okay.
Okay, so
Once
only
again, it
after
will come back to 0 then.
0, it will be initialized as 0. Then the J loop happens. Inside the J loop, I'm setting the flag. And this condition is also after the J loop only, right?
Okay. Okay.
Understood, no?
Yes. Yes. Yes.
Okay. Next, insertion sort. So in the insertion sort, um, okay, I'll just give a overall idea about insertion sort, and then we'll go to insertion sort illustration. So in insertion sort, what we're going to do is we have a sorted array. Okay, suppose we have a sorted array, and we are trying to insert a new element inside this sorted array. Okay, now what we will do to do that? We will search for the correct position, right? Okay, suppose we have um, 5, 10, 15, 20. Okay, suppose we have 5, 10, 15, 20. This is a sorted array. In this sorted array, I want to insert 12. Now, where I would insert 12? In between
10 and
10 and
15.
15, right? Okay, so my new array will become 5, 10, 12, 15, and 20. So I'm going to find the corresponding position where to insert this new element, and then I will create a new sorted array. Understood? So this sorted array, after involving this new element, what happens? This would become the new sorted array. So like this, I keep on adding new elements to this sorted array. It keeps on building a new overall sorted array. So this is the basic idea of insertion sort. Okay. So basically what we need is we need one sorted array to perform this insertion sort. So where to go for a sorted array? So when will we know that the array is sorted definitely without doing any comparisons and all? With respect to number of elements, you can tell. When will we definitely know that?
When it's 1
Yeah, very good.
or
So if number of elements is 1, okay, it is sorted, right? So we need not do any comparisons at all. If there's only one element, then the array is definitely sorted. It might be any sorting, ascending or descending, whatever it is. Okay. So let us take an example. So let us take these elements. Now we're going to consider this 12 as a sorted array. And these are set of elements which we are going to insert on this sorted array. Okay. Now let us take a temporary variable d that is going to store the element that is going to be inserted inside this sorted array. So the first element which you're going to process is 34, right? So just put 34 inside d. So now what is this d is nothing but the ith element. Okay, so I would start from 1 and go till the end. Okay, and the inner loop, j loop is there, right? That will start from I minus 1th position and go till the end of the list. in the reverse order. Okay, so till it reaches the end, it keeps on iterating. Okay, fine. And it is J is going to point the position where this D should be inserted. Okay, fine. So let us do this process and then figure it out how this is happening. Okay. So now what you have to do is you have taken ith value and then ith element and then stored it in D. Now do a comparison between D and then A of J. Suppose if the array name is A. So don't compare with ith element and jth element. Compare the ith element with D. Okay. So now what happens is here, if D is greater than A of J, okay, then immediately stop the iteration and then come out of the iteration and then just make A of J plus 1, A of J plus 1 is equal to D. So this will happen after the iteration, J loop, after the J loop. So so where should 34 be inserted? 34 should be inserted to the next of 12 only, right? Okay. So I compared D and A of J. D was greater than A of J. So I broke out of this J loop and came out. And then I just insert D at the J plus 1 position. So now what happens? D would be inserted at J plus 1. J is 0. 0 plus 1 is 1. So in this position, 34 will be inserted. There will be just a overwriting of this algorithm, overwrite of this element. Same element is being overwritten again. That's it. So this is the first iteration. Now I got a sorted array. 12 and 34 is a sorted array. Right? Now I goes to the next position. And J will start from I minus 1th location and go till the beginning. Okay. Now what is D? The new value of D is 1.
1.
Okay. So now I have to check where this 1 should be inserted in this sorted array. Okay. So this is a sorted array. In this sorted array, I'm going to insert 1. So now what A of J comparing with D. So D is less than A of J. So what I should do is decrement J. If it is greater, immediately break. If it is lesser, decrement J. Again do a comparison. D and A of J. D is less than A of J. So decrement. So now J has reached minus 1, right? It has come out of the array. Okay, out of the index at all. Index. So now we can stop the iteration. Obviously, it will stop. You'll just iterate till 0 only. Okay. So it will stop, and after coming out of this J loop, J is minus 1, right? So what is minus 1 plus 1?
0.
Okay, sorry, I forgot one step. See, I'll repeat again. See, you compare D and A of J. So comparing D and A of J, D is less than A of J. So what you do is you move J to the A of J to the next position. Moving means just copy this value and paste it in the next position. And then decrement J. Now again do a comparison. D and A of J. So D is less than. So copy A of J to the next position. You're just moving the elements. Okay. And then decrement J. Now come out of the J loop and then do this procedure. Do this operation. A of J plus 1. So minus 1 plus 1 is 0 equal to D. So now what happens? At 0th position, D would be inserted, which is 1. Now you got the sorted array, right? So now you will insert 15. J would start from second position, second index, right? So now D is what? 15. So compare D and A of J. So D is less than A of J. So what you have to do? Okay, copy this in the next position. So 34 goes there, decrement J. So compare D and A of J, D is greater. So you have to stop. Okay, stop the iteration, break the iteration, come out, And then j is 1, right? I write the index. J is 1. So a of j plus 1, a of 2 is equal to d, 15. So here 15 would be inserted. Now we got this sorted array, right? Now coming to 2. Okay, now the value of d is 2. So j is 3, a of j is 34, right? So d is 2. So 2 and 34, d is lesser. So what do you do? Move 34 to the next position. Decrement j. A of j is 15. Comparing with d, d is lesser. So move j to the next position. Decrement j. A of j is 12. D is lesser. So move a of j to the next position. Decrement j. Now d is greater than a of j. So break. So after coming out of the loop, j is 0. So a of j plus 1 is 1. Uh, j plus 1 is 1. So at first location, 2 will be inserted. So now we have this sorted array. Understood? Now I is pointing to 45. Okay. So now new d value is 45. Compare d with 34. Okay, 45 is greater than 34. So break the loop, come out a of j plus 1. So 4 plus 1 is 5. A of 5 is 45. So in the same location, 45 will be overwritten. Okay. Now I is pointing to 40 and d is 40 now. Okay. So now 40 compare with 45. 40 is less than 45. So move 45 to the next position and then decrement j. Compare a of d with 34, 40 with 34, 34. D is greater than 34. So break. Coming out of the loop, a of j plus 1. J is 4. So 4 plus 1 is 5. So a of 5 equal to 40. That's it. So this is your insertion sort. Understood? Any doubts? Any doubts in this illustration? Shall we see the implementation? So in this implementation, like I was starting from which location for I in range? Yes, I was starting from the first location, right?
First.
Why we are
Yeah.
starting from first location?
12th.
Because yeah, we are considering single element array as the sorted array. So we are starting from index number 1. So 1, comma, we are going till the last element. So which is n. And j loop, what is the start of j loop? And as well as is going in reverse. So what is the start?
0.
No, it's going in reverse, right? End is 0.
N. N.
No, not n. It varies, right? Depending on I. If I was pointing to fourth location, j was starting from 3.
Yes. Yes.
So it is depending on I only, right? I minus
1.
1. Yeah. So I minus 1, comma 0. Okay, so you need not mention the last value, and you are going to mention the step size as okay, last value has to be mentioned. I think should be -1. Yeah, -1, and then step size is -1. Did you get this? I'm starting from I -1, going till -1 index. Okay, this is not inclusive, right? So it goes to 0 only, and then this is -1. Step size is -1. Okay, now what are we doing? We have done some comparisons, right? So when do we have to break? If D is
Equal to a of j plus
not
1.
equal to, greater than.
Sorry,
Yeah. So
greater.
if D is greater than A of J, break. Else what you have to do? We
You have
have
to
to move,
assign the
move that element to the next position, right? Yeah.
mm,
So A of J, next position means current position is J, so next position is J plus 1 is equal to A of J. That's all. So once we come out of the J loop, what should we do? This step, right? A of J plus 1 equal to D. So we haven't taken D at all, right? So D is equal to A of I. Okay. And then here A of J plus 1 is equal to D. Understood? Any doubts in this? Initially we're taking D. So that's what we did here also, right? We took the ith element and then stored it in D. And then we run a loop starting from I minus 1 till the last. Okay. So when did we break? If D is greater than A of J. So at any point, if D is greater than A of J, you just break the loop. After coming out of the loop, just put A of J plus 1 is equal to D. That is wherever J is stopping, the next position you're going to insert D. That's all. Any doubts in this? Yes. Okay. So now talking with respect to the complexity. So worst case, what happens? In the first iteration, one comparison happens, right? In the second iteration, if I starts pointing to the second element, two comparisons happen. And if I points to the third position, three comparisons happen. 4, 5. So like that goes on, right? 6, because there are 7 elements here. So this is the reverse of bubble sort, right? It started with 5, 4, 3, 2, 1. Here it is 1, 2, 3, 4, 5, 6. So if sum of n minus 1 natural numbers, it is same as order of n square. Okay, so the worst case complexity here also it is order of n square. So what is best case? Best case for insertion sort is order of n. So how it is order of n is, see here, you take a already sorted array. So let's consider this array itself. So what happens? I will take the ith element and store it in D. Every time the first iteration of the J loop itself, it will break and come out, right? Because D is
break.
greater than A of J, break. Again, 12. 12 is greater than J, break. 15 is greater than 12, break. 34 is greater than 15, break. So like that, every iteration, every I loop, inside the J loop, the first iteration itself, it will break and come out. So n times the I loop will run, and only one time the J loop will run. So n into 1 is n. So the best case is order of n. Understood? Any doubts in this? Understood why the order is best case is n? So in insertion sort, we can see without even getting a new flag variable, we're able to achieve order of n. Understood? Any doubts? Are you able to get it? Okay, fine. So now comparing with insertion sort and bubble sort, which one do you think is better? Is insertion sort better or bubble sort better? Both are having best case is order of n and worst case is order of n square. Okay, so now you have to compare with the number of operations that are happening inside the loop. So here in this, just an assignment operation is happening, right? Whereas here in this bubble sort, a swapping operation is happening. So in the last class only we saw swapping involves three operations, right? Three steps. So here in one step we are just moving it, moving that element. Whereas here we are swapping. So swapping is costly than this movement. Understood? So like because of this swapping operation, which will take additional two steps, insertion sort is better than bubble sort in a very small factor. Okay. Understood? Fine. So next is sort is selection sort. So I want you people to understand what is selection sort and come. So it is now already 6:40. So I think if I start with merge sort, it will take more time. So we can see merge sort in the next class. Okay, fine. So in today's class, yeah. So in today's class, we saw about divide and conquer. We started with divide and conquer. I told you what is divide and conquer exactly. And then we discussed about searching algorithms. Okay, two searching algorithms, linear search and binary search. We saw how to derive the complexity of a recursive problem using recurrence relation. Okay, and then we saw two sorting algorithms: selection, bubble sort, and insertion sort. Selection sort, you please come and check and come. Okay, sir, can you say a few examples where to use flag? It depends on the problem, right? Uh, See, flags are actually used to like um, just to check the flow. Okay, suppose you want to check whether a particular set of statements are running or not. So here also you can see, right? So I want to check whether flag is running or not. Sorry, swap is running or not. Swap is happening or not. So for that I used a flag like that. mm, okay, I'll think and tell you in the next class. I'll give you a few more examples where flag is used. In evox itself, you would have used, right? Few of the problems where flags are used. Will we be able to access the course content after the course completion? Yes, you will be able to access, but I don't know for how long. That is still a question mark. The COL people have to answer. I think you will be given time to finish the course. Okay. Okay, fine. So any other doubts? I think still 3 or 4 more classes are there. After that, we have 3 projects to be done, discussed. Okay. So I think this course will go till June end. Fine. So shall we wind up for today?
Yes, sir.
Okay.
Thank you, sir.
You.